Our notes for ME23063A. I'm on page 71, which is our tensile testing practical. The machines are called a houndsfield tensometer. They are essentially a student tensile machine. The sample on this particular machine is a steel sample, 5.05 millimetres in diameter, and we've put it in here in the collets to hold it in the machine. We're going to do a tensile test. So by tensile testing, it means we're going to pull it until the point that it actually breaks. During that process, we're going to look at some properties of the material and then use the actual broken test piece to determine some other properties for the material. A little bit about the machine. Essentially, it's got in here, it's got a beam over the back here. The beam pushes the fluid through some plumbing here, and it moves up and down, and the up and down gives us the actual load. So it's a primitive load cell. We have the beams, here's some other beams here, and you can see they're a matched pair, the beam to the scale, the load measuring scale. The handle up this end is turned to actually apply the load. Whilst you're applying the load, it's got a set of gearing through here, which actually turns the drum. And with the drum turning, it's actually, you can see there's different gear sets here, which means we can actually magnify what we call the extension axis. So we're going to produce a curve, and it's going to have a force axis and an extension axis. Okay, so we've got two students here. They're actually going to use the machine. So we need one student up this end to actually follow the fluid as it's rising and just push down on this cursor here. Okay, and that'll make a hole in the paper, and the other student to actually turn the handle to actually apply the load. Whilst you're applying the load, as I said, this will turn the drum around, it will rotate to actually give us our graph.
How quickly do you turn the handle?
Just a moderate speed but consistent. Okay, righto? And you push that down. Okay, yep, so push it down now so you've got a hole in it to start with. Righto?
And you just have to push it up so that it follows the mercury up. So you have to
Slide that up.
so the mercury.
Yeah, so normally just push it a little bit in front of the mercury. Yeah. Okay, no, that's all right, follow it. Right back down. So what it's got to the yield. So it's effectively yielded.
Yep.
Approaching the maximum force now. Look at the sample. It's actually necking in here, starting to neck in, so it's getting ready to break. Slightly. Yeah. Okay, so you've got a graph there now, so we can pull it off and have a little graph. go over this with a bit of biro, so you can see clearly where the graph goes. So there's our graph there of the completed tensile test. Now we're going to take the scale off the machine. We're going to mark some important numbers on it. So the force scale is in kilonewtons. Okay. So I've marked on the scale the actual force at yield and the maximum force. So the force at yield is 9.4 kilonewtons and the maximum force is 13.6 kilonewtons. The original sample diameter was 5.05 millimetres round. From there we can calculate our yield stress, our tensile stress. This sample here is a new sample, obviously that hasn't been tested. This is the sample that we've just tested. We're going to use the sample just tested to work out some measures of ductility. They are percentage elongation and percentage area. For this particular testing machine, we've actually got some little gauges that make it easy for us. New unbroken sample. Is it on 0? Okay, so it tells us the elongation is about 34%. Again, new sample. It's the original diameter. Take our broken sample, put it in. It's our reduced diameter there. It's about 56%. Okay, so that's our elongation and reduction of area.